The last time we had almost reached to the definition of the displacement vector, and today we will finally reach there. Let me review what we had done. We had a material, some non-conducting material, a uniform electric field is applied, and because this material is made of atoms, the negative charge in the cloud of the electrons moves in the direction of the electric field, and so there is a layer of negative charge at the top, a layer of positive charge at the bottom, and we have already worked out that if you have equal amounts of negative and positive charge, a uniform electric field appears that is in the opposite direction. This is what I will call an induced electric field. Now, how much was this induced electric field? Well, we worked that out. We said that supposing the slab of electrons got shifted upwards due to this electric field, by how much will it get shifted? It gets shifted upwards by an amount d, where d is, you have the nucleus, you have the net electron cloud, and they are displaced with respect to each other. That distance is d. So, you take this distance d, multiply d by the charge of the electron with a minus sign, and then you multiply it by the number of electrons per unit volume, that is the number density. That gives you the amount of charge per unit area that is present. Why? Because minus E is the charge and n into d is the volume. So, this is the charge density. So, there is a charge density equal to minus n E d, and there is a charge density equal to plus n E d at the bottom, and it is this charge density that causes an electric field. We can apply Gauss's law. Supposing we had only this charge, no applied electric field, then Gauss's law tells us there is no electric field outside, there is an electric field inside, and the electric field inside is directly related to the amount of charge enclosed. So, this is equal to E induced or E ind. So, E ind is negative in sign, that is, it is pointing upwards. Now, this is not very useful because we do not know d. We know the charge of the electron, we know the number density of electrons in the material, but we do not know d. However, from our model of what happens to an electron cloud, we know that the stronger the applied electric field, the more this cloud shifts. So, we can plot saying applied electric field E external, and we can plot the amount of d, and we find that it is approximately linear. It is very linear for small values of applied electric field, but for larger values it deviates from being linear. So, in this region where it is in fact truly linear, we can treat this d and therefore, this induced electric field as proportional to the applied electric field. Now, there are materials where you can apply an electric field this way and the induced electric field will be in some other direction. These are called anisotropic materials. We will not touch anisotropic materials right now, So, we will assume that if you apply an electric field, the electron cloud shifts in the direction, opposite direction to the electric field. An anisotropic material would be one where I have an electric field this way, my nucleus is here, my electron cloud shifted in this direction. Even though the electric field is this way, the electron cloud did not shift directly backwards, it shifted sideways. This can happen because of a crystal structure of the material, and these are more complicated materials, but very, very important from an engineering point of view. For now, we will decide to study only systems where the induced electric field is exactly opposite in direction to the applied electric field. So, we can write E induced is equal to minus E n times d, and d is a vector now, is equal to some coefficient, I called it alpha last time, times the external applied electric field. This alpha is clearly negative because the induced electric field tries to cancel the external electric field. Let us get back to the original problem. I have a material and I apply an electric field. Due to this applied electric field, some kind of charge has developed. Actually, charge is developed everywhere, but the only place where charge does not cancel out is the top and the bottom. Now, supposing we knew how much this charge was. If we knew exactly what this charge was, we can actually solve for the electric field. We can say that the electric field E is equal to 1 over 4 pi epsilon naught times the total charge, integral of rho total divided by r minus r prime squared times r minus r prime unit vector dV. What I mean by this is, if I actually knew how much bound charge was developed by the applied electric field, I can go back to Coulomb's law, and Coulomb's law is always correct if I knew all the charge. The only problem is I do not know all the charge, all right. Now, there is one other thing. If I take this E induced, it is proportional to the electric field. So, I can take the divergence of both. Now, this expression tells me divergence of E is equal to the total charge density divided by epsilon naught. No matter whether there is a material or not, if I could somehow calculate the total charge, not just the charge I put there, but including the charge that is induced, then this is true. Let me take divergence of this. So, if I take divergence of this equation, I will get divergence of E induced is equal to divergence of alpha E. Which can be broken, though it is not very useful to do it, alpha times divergence of E plus E dot grad alpha. The only reason for doing it is, we can see that divergence of E is already related to something, the rho total over epsilon naught. So, you could write it as alpha rho total over epsilon naught plus E dot gradient alpha. Now, what is more useful is to look at this picture, the picture we have been drawing for a while now. For example, take a look at this and say that the only place charge develops is where this factor alpha changes abruptly, because if you look out here, this is air, alpha equals 0, there is no induced charge. This is my glass, alpha equals something. This is air again, alpha equals 0. So, if you look, wherever alpha is constant, nothing is happening, but where alpha is 0, changing from constant to 0, that is where there is charge developing. So, we could think of this as representing a charge itself. Wherever E induced changes abruptly, that is a place where there must be charge, and this picture agrees there, because if I apply Gauss's law, E induced went from 0 to positive, there is charge enclosed. E induced remained constant, there is no charge enclosed. E induced went from positive to 0, there is negative charge enclosed. So, it looks like divergence of E induced represents some sort of charge. In fact, it represents the induced charge. So, I will write these two equations. Divergence of E is equal to total charge density over epsilon naught. Divergence of E induced is equal to rho bound over epsilon naught. The B means this is the induced charge. So, it is bound to the individual atoms of the material. It is not something we place there, it is something that appears only in the presence of an applied field. The problem in engineering, the problem in all of electromagnetics is we do not know it. This rho bound is simply not known to us. So, what we are going to do is, instead of working with rho total, which is a sum of the charges we have placed, which I am calling rho free, and the induced charges rho bound, or working with E induced, which deals with rho bound, I would like to work with some kind of electric field that only relates to rho free. That is the only rho I know about. The remaining rhos are self consistently to be determined. So, I am going to take the difference, because I can see I can cancel out rho bound. So, I will take divergence of E minus E induced is equal to rho free divided by epsilon naught. What is more, we have already written down that E induced is equal to sum alpha times E. Now, alpha is not the symbol that is used, but I am just keeping it there for a placeholder. So, I can write this as divergence of, and I am going to take this epsilon naught to the other side, it is harmless, it is a constant, times 1 plus alpha times the electric field is equal to rho free. Now, this probably looks like magic, but what it is actually a kind of a fancy sort of cheating, and I will go over it again so that you feel more comfortable with what we have done. But what we have achieved as a result of all this is we have identified a new kind of field. It is related to the electric field, but it has some material properties in it. This alpha represents the relation between the applied field and the induced field. In other words, it is talking about the slope of this line. Now, it's a electric field like quantity, because it depends on the electric field, but it is multiplied through by some material properties, and its divergence is equal to rho f only. This quantity is what we call the displacement vector. The name is purely historical, but its usefulness is extremely high, because if you write this equation down, you know the right hand side completely. You place that charge there. So, you know exactly what charge you have placed, and therefore, you know mostly what this vector field is going to look like. The problem of course is then how from this displacement vector do I obtain the electric field. Now, this all comes down to finding this alpha, and if you look back to see what is this alpha, E induced is nothing but minus E induced is nothing but minus E n d. Okay, this is the Q bound, and from Gauss's law we found that E is equal to minus E n d, and E and n are material. E is a constant, n is just the number of atoms per unit volume. D has to do with the material's tendency to deform in the presence of an electric field. So, all of this is can be put down as fixed material property of the medium. So, what does that mean? It means that the relation between D and E is something we can put down in a handbook and just use. It is not something to be solved for. If I make a plastic, then the manufacturer of the plastic will subject that plastic to tests. He will find out if I apply 1 volt, how much is the induced charge. If I put 2 volts, how much is the induced charge, and he will give me a plot of E induced versus E. And if the material is a linear material, that is E induced is proportional to E, he will give me this whole number, and this number is called the dielectric constant. Now, let us go back and review. If we apply an electric field to a material, induced charges appear. These induced charges for a slab like this form at the top and the bottom of the material. In the middle they tend to cancel out. If you ask how much is formed, it has to do with the thickness of this layer of charge. The thickness has to do with the amount the electron cloud shifted, and the amount the electron cloud shifted experimentally has been seen to be linear. There is no proof that it always has to be linear. In fact, it does not always have to be linear. There are nonlinear portions to this curve, but where most engineering applications happen, it is a linear curve. So, I can write the induced electric field as something times the applied electric field. Start with this. This is the first equation. Now, the second thing is, if I knew every charge present in the entire universe, including the charges I deliberately place and the charges that are induced on surfaces of materials in the bulk of materials, if I knew all those charges, then Coulomb's law is still true, because Coulomb's law says if I knew all the charges, just write down rho over r squared with the appropriate direction and integrate over all space, and from Coulomb's law we can always derive the divergence theorem. Divergence E equals the same charge density divided by epsilon naught. So, now we have this equation, where this total charge is rho free plus rho brown, that is the charge we placed plus the charge that was induced. Now, the induced electric field is clearly related to the induced charge, because that is where it came from. So, divergence of E induced is nothing but the bound charge divided by epsilon naught, but we do not know what it is. But I take these two equations and I say I can eliminate rho bound. Just subtract the two equations, I have got rid of rho bound, and that is what I do. I take divergence of E minus E induced, and it is only related to rho free. And when I write out E induced in terms of the applied electric field, I get this equation: divergence of some other vector is only equal to rho free. It is a crucial equation, and it's a bit of a tricky equation, in the sense that you can just write it down and use it without realizing what it represents. Let us take an immediate example and see just how this applies. It is a trivial example, but it is worth understanding. I have a charge q and I place it inside a sphere. This is at the center. Here it is air, here it is glass, and here it is air. The inner radius of the glass is A, the outer radius is B. I want to know what is the electric field and the potential as a function of R. All right. Now, there are two ways of going about it. One way of going about it is to say, well, up to this point I am completely in air. So, I know the electric field from 0 to A. Nothing but Coulomb's law. Now, this electric field, when it enters this material, is going to cause induced charges, and I can try and write down a relation between E induced and the applied electric field, and I can try to work out what is going to happen inside the material. However, there is an easier way of going about it. The easier way is to simply say divergence D is equal to rho free. So, if I apply Gauss's law not to the electric field but to D, I can take any radius sphere, the integral of divergence D is nothing but surface integral over that surface of that volume D dot ds. But this is equal to volume integral of rho free. Now, I do not know what is happening inside this material, but whatever is happening inside this material is induced response, that is, the charges are all induced. The only free charge I know about is this q. So, it is equal to q. It is a spherically symmetric problem. So, surface integral d dot ds is nothing but four pi r squared d of r. D in the r direction, which is a function of r. It is equal to q. So, I know D. D has only an r coordinate, and the dr is q over 4 pi r squared. I have not solved anything else, but regardless of what the dielectric constant of glass is, regardless of whether I have one glass or many glasses, as long as the problem is symmetric in all directions, spherically symmetric, I have already solved the problem. I have found out d sub r. How does it help me? Well, I will look up my handbook for the glass and I will find out that this handbook tells me epsilon glass is equal to 2.25, or it could be 2.5, or it could be 3. It is some number. It is written by the manufacturer of the glass. So, in that case, I know that d sub r is equal to epsilon glass E sub r. So, let us just look at the plot and make it clearer. This is the radial direction, this is A, this is B. If I plot d, d is nothing but q over 4 pi epsilon, sorry, q over 4 pi r squared. So, it is going to be 1 over r squared. This is d. What is E? Well, instead of talking about what is E, I am going to talk about epsilon naught E. Epsilon naught E is going to be identical to d in these two regions. But in this region where there is glass, I know that epsilon naught E r is equal to d r divided by 2.25. So, this part of the curve alone is going to be a smaller value. So, this is epsilon naught E r. What has happened is surface charge is developed here and surface charge is developed here, so that the electric field has been reduced, the applied electric field has been reduced by some induced electric field. So, the net electric field is smaller inside the material than what you would expect it to be. Once I have got this electric field, then getting the potential is easy. Potential phi is equal to integral from from infinity, or I should say from r to infinity of E r dr, which is going to be equal to q over 4 pi epsilon naught r for r greater than b, because this is nothing but Coulomb's law up to here. For r less than b is going to be q over 4 pi epsilon naught b, that is the value at this point, plus the integral of this curve, because this is what the electric field is. So, there will be q over 4 pi epsilon, not epsilon naught, times 1 over r minus 1 over b. This is for A less than r less than b. Similarly, when you go inside r equals a. The point of this example was to show you the usefulness of displacement vector. It is not just a arbitrary field that we invented. We created the displacement vector because when we worked out what divergence E is, we find divergence E contains an unknown charge. So, we constructed a field which depends only on known charge. Now, this field therefore is complicated. It is related not to Coulomb's law, but to something else. Luckily, for linear materials, the relation between D and E is very straightforward. D and E are related to local material properties, and that is very important. You can see here in this picture, the material properties are changing. I have air, glass, air. However, D in here, D is equal to epsilon naught E. Out here, D is equal to epsilon naught into 2.25 into E, and D is equal to epsilon naught into E. So, point by point, the relationship between D and E is only through a different constant. So, the advantage of this is I have got a new field which is essentially the electric field. If I knew that field, I know the electric field, but this new field satisfies a very simple equation. It satisfies an equation whose right hand side I know completely, and that is an enormous advantage, and you can see it in this example, because I know Q, I do not know the induced charge, but even so I found the answer. All right. Now, I want to go on to one more problem, and that problem is, supposing I had my slab and I had the electric field coming at it. We worked out that there is a induced charge, and we know that there is a reduced electric field. Now, if we apply Gauss's law, we have an incoming electric field and an electric field inside the material. So, I will call this E2, I will call this E1. So, E2 minus E1, it is normal, so I do not have to keep the vector notation, is equal to rho bound divided by epsilon naught. Is that clear? That is, the amount of induced charge is the amount by which the electric field reduced. But I know that this E1, this E2 is related to the displacement vector, because if I look at the displacement vector, nothing changed. Displacement vector did not even notice this material, because there is no free charge, there is only bound charge. So, we know that if we scaled up this second electric field by the dielectric constant epsilon of the material, and we scaled up E1 by the dielectric constant of air. Okay, so, this is nothing but D2, this is nothing but D1. These two can't really be any different, because the same Gauss's law I can apply to divergence D. I can apply divergence D is equal to rho free, and I know that rho free is 0. I have not placed any charge there. Whatever charge has developed because it was induced. So, I know that these two must be equal, because if they are not equal, I would not get 0 when I worked out the total amount of enclosed charge. Let me repeat, because I think this is a subtle point. the amount of electric field entering and the amount of electric field leaving a Gaussian cylinder, an imaginary cylinder, is not equal, which means there is charge enclosed. How much charge is that? That is nothing but the induced charge. But if I apply the same thinking to D, then I have that D2 minus D1 is equal to rho free divided by epsilon naught, but rho free is 0, so it is equal to 0. So, we get this special condition. If you want to be more accurate, and we do, what we should say is that supposing the electric field is coming at some angle, we do not exactly know what angle the electric field will be inside. We know that it will be less. We can draw a cylinder, and when we draw the cylinder, if this direction is z, E2z minus E1z would be rho bound over epsilon naught. It is only the normal component that matters. If you look at the sideways component, there is flux entering, but the same flux will leave. So, only the top and bottom contribute. Similarly, when we do the argument here, you get D2z minus D1z is equal to 0, or D2z is equal to D1z. The way this is put is the normal component of D is continuous across interfaces. I say it is continuous across interfaces, but it is really continuous everywhere. Okay? It is continuous here also, it is continuous there also, but that is assumed to be true. But in a place where things are changing abruptly, you can see that the electric field is not continuous. E2 is not equal to E1. Why? Because there is this rho bound. If E2 were equal to E1, E2z minus E1z would be 0, but instead E2z minus E1z is equal to the induced charge divided by epsilon naught. However, even in such places, the displacement vector is continuous. For the displacement vector to be not continuous, you should have placed charge on this surface. So, let us just emphasize that and go on to next point. Supposing I had a slab with an epsilon, say glass, epsilon equals 2.25, and supposing I deliberately put charge. How much charge? Let us say 10 to the minus 6 coulombs per meter squared, some charge I have put. So, I know this charge, and therefore, this charge is rho free, because it is charge I can account for. It is present even if there is no applied electric field. Now, I apply an electric field. This applied electric field will create an induced charge. So, there will be a small amount of negative charge and small amount of positive charge. So, on the top, after this negative charge and this positive charge combine, these two will cancel. So, what you will be left with is a little bit of negative charge. When you try to work out this problem, you will have divergence D is equal to rho free, which means D2z minus d1z is equal to rho free. But rho free is no longer 0, rho free is 10 to the minus 6 coulomb per meter square. So, you will find that now your displacement vector is not continuous. It is not continuous because we deliberately put charge there. If we had not put charge there, then we would have had a continuous displacement vector. There are quite a few problems where working with displacement vector will actually simplify your analysis, and that is why it is an extremely important formula. Now, let me remind you of the other condition that we always have been using, which is that integral E dot dl from any point to any point is independent of path. And I mentioned in a class earlier that if I have a point 2 and a point 1 and I take two different paths, going from 1 to 2 is like minus of going from 2 to 1. So, this is nothing but integral 1 to 2 E dot dl minus integral 2 to 1 E dot dl is equal to 0. Okay, sorry, plus integral 2 to 1 is equal to E dot is equal to 0, or if I take any loop whatsoever and integrate E around that loop, I get 0. This statement which we made in the very beginning to obtain potential and this statement are identical. They are saying the same thing. What I am saying is, I will go this way and then I will come back this way. Since both gave me the same answer, adding up the two answers, this is the negative. So, this is nothing but integral 1 to 2 E dot dl minus integral 1 to 2 E dot dl equals 0. But this is a very interesting equation, because supposing I had my slab and let us say my electric field, I have got a sloping electric field and I want to know what this electric field is going to do. It is going to do something. What I will do is I will take a loop like this and I will try to integrate E dot dl on this loop this way. The vertical pieces I will keep very, very thin. So, I have only large horizontal pieces, and if I take this large horizontal piece, what I get, I will call this side 1, this side 2, I will get E1, this direction is z, this direction is x. So, E1x times dl minus E2x times dl is equal to 0. That is, the vertical parts do not contribute much because they are very thin. E1, the x component multiplied by the length of this, minus E2 x component multiplied by the length is equal to 0. That is what this equation says, or it says E1x is equal to E2x. So, I have two equations and let me put them prominently. I have that D normal is continuous and E tangential is continuous. These are the equations we have which describe everything we know from the start of this course. From the start, we obtained that if you have charges, you can derive from the electric field a potential, and the relation is electric field is minus the gradient of potential. From whatever we have done now, we know that there is a new field, a very useful field called displacement vector, which is the electric field times the local dielectric constant. Epsilon is dielectric constant. Furthermore, looking at the displacement vector and applying Gauss's law, we know that the normal component at an interface of D is continuous. And looking at the fact that the electric field can be derived from potential through E equals integral minus integral 1 to 2 of phi dl, sorry, phi is equal to of E dot dl. Using this, I have also obtained electric field tangential component is continuous. Let me finish the class by trying and using these equations. Supposing I have a slab with epsilon and I have an electric field that is arriving at a slope. This angle is theta. So, the normal electric field E normal is equal to the magnitude of E, say the magnitude is E naught cos theta, and E tangential is equal to E naught sin theta. So, this is E normal, this is E tangential. Now, I know that if this is E naught and this is E 1, I know that E naught cos theta times epsilon naught, that is the normal component of D, is equal to epsilon times E 1 times cos theta. Whereas, I also know that E naught times sin theta is equal to E 1 times sin theta 1. So, I have two unknowns, E naught, E 1, sorry, E naught is known, E 1 and cos theta 1. I have two equations. If I divide these two equations, I will get epsilon naught tan theta is equal to epsilon naught inverse epsilon inverse tan theta 1. All I have done is I have divided this equation by this equation. So, sin theta over cos theta is tan theta, sin theta 1 over cos theta 1 is tan theta 1, and epsilon naught and epsilon go into the denominator. So, I put epsilon naught to the power of minus 1 and epsilon to the power of minus 1. This is not quite the same thing, but it is like Snell's law, essentially saying the same thing. Now, we can also work out what happens to E 1 itself. For that, all we need to do is we need to eliminate the theta 1. So, supposing we divide the first equation by epsilon, square it, square the second equation and add them up. What do you get? the right hand side will be E1 squared cos squared theta 1 plus E1 squared sin squared theta 1. Cos squared theta 1 plus sin squared theta 1 is 1. So, it is equal to E1 squared. But what happens on the left hand side? I divided this equation by epsilon. So, I get epsilon naught over epsilon times E naught whole squared cos squared theta plus E naught squared sin squared theta. So, it is a mess here, but the mess does not matter. I know what theta is, I know what E naught is. So, left hand side is a known thing, is equal to E1 square. So, essentially if you look at what this is saying, it is saying that the portion that is tangential, portion that is along x does not change, it contributes fully to E1, but the portion that is pointing into the slab, that part gets reduced in the proportion epsilon naught over epsilon. So, if you finally solve this, you get E1 is equal to E naught square root of epsilon naught over epsilon 1 squared cos squared theta plus sin squared theta. So, if I had normal incidence, which is theta equals 0, sin theta goes off, cos theta is 1, that will say E1 equals epsilon naught over epsilon 1 E naught. So, the electric field inside the material reduces in proportion to the dielectric constant, which is exactly what we had come up with earlier, because we found that E induced was proportional to the applied electric field, and the quantity we came out with, the displacement vector, was E minus E induced. So, obviously, if D is continuous, then you must have a reduction in E wherever the dielectric constant is large. Whereas, if theta is large, then what will start happening is this term will dominate this term, and you will have that E1 is equal to E naught. This example should tell you is sort of an introduction to the idea of what we call matching conditions. And the equations here, these two are matching conditions for electrostatics, namely the normal component of D is continuous, tangential component of E is continuous. This more or less establishes all the building blocks we need to solve problems in electrostatics.